I found a love for me. Well, darling, just dive right. I found a love for me. I found a love for me. Well, darling, just dive right in. Follow my lead. Well, I found a girl, beautiful and sweet. Well, I never knew you were the someone waiting for me. 'Cause we were just kids when we fell in love, not knowing what it. I found a love for me. Well, darling, just dive right in and follow my lead. Well, I found a girl, beautiful and sweet. Well, I never knew you were the someone waiting for me.
All right, so welcome to our first lecture on performance. And I'm sorry that unfortunately, well, to be honest, like last Thursday was actually my very first lecture at UCR without a mask, but it turns out, well, you know, sometimes wearing a mask is probably a better choice for people who never caught COVID like me. And the other thing is, you know, ironically, last Thursday was actually also the anniversary of my 4th dose of Moderna, which is just right after a year. And I was thinking about if I should get a booster shot, but apparently I should do it earlier. So, you know, what all that tells us is that, okay, if there is something in your mind that you think you should do right now, you should act on right now. So for example, if you think you should start working on the assignment, you should start working on it. If you think you should enroll in the class, do it as early as possible. All right, so set it aside. What we are going to talk about today is performance. But again, I mentioned to you guys, it's very important that we get this big picture as always in our mind. So first of all, what's the big picture of computer architecture? As we talked in the last lecture, every computer that we are having right now is a von Neumann architecture based computer. So what does that mean by von Neumann architecture? Is a computer is consisting of the 3 main components of processor, memory, and storage. And how the computer uses 3 components is that once we generated a program, the program, which means a set of instructions that you want a computer to do, a set of data that you want a computer to operate on, and you put them in a storage device first. And when you want to use the computer to run that program, load everything to the memory. When I say everything, it includes instructions and data. And then your processor will fetch the instructions line by line from, well, instructions from the very beginning of the program and look into what the program wants the computer to do. If the instruction is wanting us to manipulate data, then that's the time we are going to access data memory. Otherwise, the instruction would typically move to the next one or jump to another one based on the control flow once the instruction is done with its job. And the beauty of von Neumann architecture is that without reconfiguring the hardware, simply by changing what's inside the memory, the computer can totally act differently. So through your assignment 1, you have probably experienced a lot how a program being converted into a set of binaries that we mentioned. But typically what would happen is that the programming language frameworks, for example, your compiler, will analyze the elements in your programming language. The program source code that you composed, and then translate them into corresponding machine instructions, which give you the instruction part. And also for those static data that you assigned in the very beginning, we'll put it in the data section of your code. So those are the 2 basic sections of a program. And okay, so most of the time we thought the program should behave as what we have in an algorithm complexity. However, as we have the demo last lecture, right, which a lot of you still probably don't even get it at this point, and don't worry about it. I don't want you to know the answer too early right now, because otherwise you probably would drop the course, right? So one thing that we found is that, well, for this program, if the option is 1, then the complexity of the total program would be order n log n, and otherwise it would be order n. So intuitively, we should avoid this sorting operation. However, through our last demo, it shows us that with this sorting operation, it sounds like we are doing something redundant. However, it actually helps us to achieve 5 times better performance. And complexity is not just one thing that's misleading in performance programming, but also another thing is that complexity, or a lot of theorists, they forgot that the computer architecture is not an ideal machine in a way that the processor speed and memory speed is already having a huge gap. So it's very important that when you are doing your programming, you should consider those factors. And finally, we are interfacing the problem with mismatching application demand and general purpose processing. No matter how good we try to improve our process technology, the hardware improvement is very limited, not because of the slowing down of Moore's law, but because of the power scaling issue. So turns out that as a software programmer, if you cannot find a way to control the growth of your demand, or you cannot find a way to better utilize the underlying hardware, then there's no way we can make our product, our features efficient. So that's why we want to be in this course. So today we are going to start our discussion on performance, but it's always a good idea to put everybody on the same page about performance. So some of you asking about what's the reason behind a huge gap. Why can't we just increase the speed of memory modules? And the answer is the process technology won't allow us to do that. The circuit technology is very limited, and the memory itself, because it's capacitance based, so it's almost impossible to make the memory scale as fast as the processor. So it's the physics limitation, not the cost effective. So even for SRAM technology, it cannot fully match your processor performance right now. So memory is going to be slow, and we don't see a way to make it faster. There are some new technologies, but they are not very mature yet, not very stable. So cost effective is one issue, and the other thing is potentially the reliability of those memory cells. Hopefully those answer the questions from people online. And the other thing is that if you have questions, please raise your hand, and so that and also you can unmute yourself so that I know what's going on, because most of the time when I look into my screen, I probably won't be able to pay attention to that. All right, so today we are going to start our discussion on definition of performance and performance equation and talk about what it affects each factor in performance. All right. So first of all, right, you need a definition of performance. So for example, right, do you believe UCR is the best university in the United States? Do you believe that? I want to hear some voice. Is there anyone in the classroom right now?
Yeah. Hi, yeah, we're here.
Okay, how many of you are in the classroom right now?
I count 11.
Okay, wow, surprisingly. Okay, so a lot of you think it's the best university, but why? Can you give me some reason? Why do you think it's the best university? Okay, some of you say no, right? Why? Some of you say you just like to believe. What else? You know, that's not science. Social mobility. Okay, because I'm here. Okay, because you guys have me. Okay, thanks a lot. Okay, so the thing is that, right? To be honest, if we rank the National University, Princeton is probably the best one. Computer science, everyone will think about MIT, right? And well, where I graduated, UC San Diego also claimed that they are ranked #1, and UC Riverside for sure for social mobility, right? So every school that is good enough may be able to find a way to claim that they are the best. So what really important is that we have to put everybody on the same page. When I'm talking about what does that really mean by better performance, there is a guideline. So let me give you an example, right? So Bard and ChatGPT, right? So let's start. So this right now we're going to have our very first peer instruction question, and I'm encouraging everyone to look this example carefully. So right now I'm asking Bard and ChatGPT for the same question. Okay, so the question is, how important is computer architecture in computer science? So as you can tell, within 6 seconds, we got 182 words from Bard. And within 18 seconds, we got 170 words as the complete answer from ChatGPT. So based on this, here we are going to have our very first peer instruction question. So again, as we mentioned, we are going to use peer instruction, and you need to use poll everywhere. And right now, let's go through this process again. So first of all, make sure that you log into poll everywhere through the app or the website within your UCR account, and you will have at least 90 seconds to let me know your thought about this answer. And if you don't have the address, then you can use the QR code that I put on the slide and log in with your mobile app or your mobile phone or anything that you can think of. Go into this address, log in with your UCR account, and start thinking individually. Okay, I have quite a few answers, so let's wrap up in 15 seconds. All right, 5, 4, 3, 2, 1. Time is up. Okay, so after the first round of voting, okay, so here we go, right? So we got various different answers. So most of you think is either C or D. So why don't you? So here's the purpose of peer instruction, because it's so difficult for everyone to think. Well, sometimes these questions when I design it, I want to encourage discussion. So they are tricky for a purpose. So and it's definitely a question that I like to design in a way that would lead to good discussions. So it's very important that you guys can go into discussion with your surroundings if you are in a classroom for 90 seconds. And if you are not in a classroom right now, and if you are Zooming online, what you need to do is that check the chat. And I put a file that give you what's the current give you the file regarding the question that we are asking right now. And then what I will be doing is I will put you guys in breakout rooms, so that people in the same breakout room can potentially discuss with each other. But give me a second. I don't see the oh, here we go. All right, so I will so we have how many of you? So we have 40 online. So I will put okay, I will give you guys maybe 4 breakout rooms. So please open the file in the chat and discuss with people for maybe another 90 seconds. Go. Okay, when you come back, don't forget to vote again, because we want to see what people think after you are done with your discussion. All right, so after you are back, please use the 15 minutes to 15 seconds to put your answers in. 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see. What do you guys think after discussion? Well, after discussion, it still doesn't see too much of the difference. So that's why you guys need me, or we need a whole classroom discussion. So can I have someone volunteer to tell me what your group's thoughts is about?
Right. Go ahead.
Okay, what's your name?
Nurla.
Okay, what do you think?
I think response time and end-to-end latency, from the information that we show in from the file in the chat, we can say like
So
response
response
time and
end-to-end latency.
But
Okay.
I don't think we can say something about the quality of results and also throughput, because it's about like how efficient we use the hardware, how many tasks we run per second.
Okay, so what about others? So some of you think it's 3, right? So you have 2.
Yes.
Hi, this is Siddhant here. I chose 3. I was thinking response time, end-to-end latency, and throughput as well. Because in our group we were thinking throughput as number of words generated per second. So since since the end-to-end latency for BARD was less than ChatGPT, so by default the throughput should also be better for BARD.
Okay. So what else? So Nolan, do you agree with throughput?
Actually, I think the throughput of the BARD can be more like better than ChatGPT, but the information that we have in the chat, I think it doesn't tell us.
Are you sure? Because we already have the experiments, right? So what's the definition of throughput?
Number of tasks per second.
Number of what per second?
Tasks done per second.
Okay, so how many seconds in the previous example we have finished the question answer for BARD?
6 seconds.
6 seconds. How about ChatGPT?
18.
So who has better throughput?
BARD.
Right. So, well, throughput is something I would say BARD wins a lot for this case. How about the end-to-end latency?
BARD.
It's also BARD, right?
Yes.
So, two things that we have question about is the response time. So, okay, so based on your understanding about response time, what's the definition of response time? Or say, how do you define responsiveness?
I think it's the wait time that we get the first word from BARD or ChatGPT.
Okay, so in this way, who has better response time?
I think it's BARD.
Are you sure?
I
Let's
think we
go
can,
back and look at the demo
I
again.
think
can we
we need
just
to
look
look.
at that slide again?
Yes.
Okay, so I start this demo now. Who has better response time?
ChatGPT.
And GPT.
Okay,
Yes.
right.
ChatGPT,
So
yes.
here's the thing. Okay, every slide it matters. So sometimes be careful about the slides. Some of you were thinking about, well, professor's just doing some meaningless demo, but actually that matters, right? So okay, so ChatGPT has better response time, but worse throughput, end-to-end latency, quality of the results, hard to judge, right? So again, right, who is better, right? Because this is like a forever war that we can see Google and OpenAI is going to have for the foreseeable future, right? So you definitely want to say, well, when somebody is talking about like BART is better than ChatGPT. You have to make sure that you guys are on the same page for what metrics are you talking about, right? So if you're talking about throughput, maybe. If you're talking about end-to-end latency, maybe. If you're talking about response time, no, I think ChatGPT is probably better. Quality of a result, that's not too hard to judge. All right, so it's really important that when we talk about performance, we have to know a right metrics to compare against each other. Should we use latency? Should we use throughput? Should we compare quality of result? And everyone needs to be compare on the same page, on the same metrics, under almost the same criteria. So no cheating, everyone is under the same customs, except for the one change that you want to compare, right? So that's another thing important about a fair performance comparison. And finally, there is a formal definition of quantitative comparison. Like when I say mine is better than you, by how much, right? Maybe not that much, maybe a lot, right? So we need a quantitative comparison. So those are the issues that we want to discuss today. So first of all, what people typically would like their things to be done as early as possible. We don't want people to start answering email, but not able to solve the question, not able to solve the problem. So what we actually want is end-to-end latency in most of the case. So and by end-to-end latency, it means that the first second, the computer start running the program, and the last second it finished the program. So that's the end-to-end latency definition. And through the reading, you should already know the classic CPU performance equation. So this slide is actually a recap of CPU performance equation. So I want you to spend maybe 2 or 3 minutes to give me the answers through your poll everywhere. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to, wow, so we got a pretty good advocator, good amount of advocator on the answer B. So since everyone has a pretty good consensus on answer B, so can I have some of you walk through this example and tell us how did you get the answer as B? Okay, Nolan, I see you unmute yourself. Do you want to share?
Yes. So Actually, I just use the formula, like the total
Okay, what's the formula? What's the formula, right? So thinking about right now, you are answering a midterm, right? So you cannot say, oh, well, I just use the formula. You have to tell me what the formula looks like.
Yeah. So the formula is about the total execution time. So it equals the number of instructions, like instruction count times cycle per instruction, and times cycle time. So
Okay.
yeah, just for like type A, it's gonna be 1/5 of total instructions, and for type B, it's gonna be 1/5, and type C the rest of them. And then we're going to add them up.
Okay, so that's my way of calculating it. I like to get the average CPI like this, and again, as you said, right, there is a oops. So again, well, so thanks a lot for your answer, right? So first of all, right, through the reading, you should know in computer architecture, this book in particular, this is how we define performance. Performance is 1 over the execution time, and the execution time is the total number of instructions in your program, how many cycles on average per instruction, and the seconds per cycle. And the seconds per cycle is called cycle time, or say the flip of your frequency. And typically when we say 1 gigahertz, that's probably not 1 nanosecond, right? So it's actually the simplest kind of performance, and why it's calculated in this way, right? It's pretty much based on the von Neumann architecture, as we mentioned. Every time we execute one instructions, and one instruction, how many instructions that your program has, and how much time it takes to execute each instruction on average, that actually gives you the performance equation. So that's why it ends up that for this question, we have an answer that is 2.5 seconds. Okay, so this is the very basic one. You probably already know this when you were an undergrad. So now let's give you some more example that's connecting to this equation to the real life. So what if I have this pieces of a code, and then can you tell me how much time would it take to execute the code snippet? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see. Okay, so this time we got some deviation on the answer. So why don't you guys talk to each other for maybe another 90 seconds, and some of you, so for people online, please open up the file that I have in the chat, and let's discuss in a breakout room again, and let me know And don't forget to vote when you come back. All right. All right. Sorry, I just figured out that I'm muted. So it seems like after the vote, everyone is on the same page, almost on the same page. So to convince me that you guys really did get the core of the question, can someone share your thoughts with me? All right, Revan.
I can, yeah. So if the count is set to 1 billion instruction, 1 billion, then this loop is actually like loop is iterated 1 billion times. So let's say we have this move instruction. This move instruction is a memory instruction. So
Right.
if the count is 1, then 1 billion instruction takes 4 cycle. Then add and compare. These are other instructions. They take 1 cycle. So 3 billion instruction takes 1 cycle. And this jump instruction is branch instruction, and 1 billion instruction takes 3 cycles. So this question is actually simplified to the previous question. So we have 1 billion instructions that takes 3 cycles, 3 billion instructions that takes 1 cycle, and 1 billion instruction takes 4 cycles. So applying the execution time formula, which is instruction count times CPI times cycle time, which gives us 2.5 seconds.
Right. So again, right. So you can also consider the question in this way. So each loop we have 5 instructions, and if the count is set to this amount, so the total number of dynamic instructions, which means the total amount of instruction instances that this compiled program will generate during the runtime, is 5 times this amount. And with this 5 billion instructions that we have, right? 1 out of 5, which is 20%, is a memory instruction. 1 out of 5, another 20% is a branch instruction. Other 60% are the general purpose, general instructions. So that's pretty much the same as the previous question. So once you find this, right, this question is essentially exactly the same as the previous one. But what really this question want to convey to you is that a lot of people, they cannot even, connect the performance equation with real code, because we kind of like forget, we kind of only know that, okay, I can only count if I am given the instruction count, the CPI, and the cycle time. However, don't forget, this performance equation has a strong connection with your code. So it's totally dependent on your code and the runtime parameters you give. So even the same code, if I change the count, then the answer will be totally different. So, but that also gives you the idea about, well, the instruction count here is based on the dynamic instruction count, the total number of instruction instances that will be launched during the execution time. All right. So, we want to talk about performance because people just like to compare. Like I said, well, I said my score is better than yours. On what degree, right? So then in computer architecture, and actually the most important contribution of this particular book, the book that we are using is called Computer Architecture, a Quantitative Approach. And a quantitative approach actually means that John Hennessy and David Patterson, they define this set of ways to compare the performance and calculate the performance. So now, say that I have a machine Y and another machine X, and you can pretty much think the machine X is the same machine as and the same machine and the same program that we just ran. And now you have a machine Y, and the claim is faster than X. But can you tell me by how much Y is faster than X given the numbers in the table? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the first round, we got to see very diverse answers. It's A, B, C, D, which I love. So no matter you are in person or online, please right now open the file or find people around you to discuss the answer. And then don't forget to vote again when you are back. So Ev, is people in person indeed discussing?
There's some discussion. Some people are contemplating on their own.
Okay. So can I hear some voice from people in person later?
Sure. Would anyone like to?
Like we can have someone in person to share the thoughts with us.
Okay, I'll just pick one at random.
Or someone who is volunteering to do that.
Okay, that's better.
All right, so for those of you who are back, don't forget to vote in 15 seconds. All right, 5, 4, 3, 2, 1. Time is up. Okay, after discussion, right? So it seems like the discussion does help a little bit. So we got two answers that are popular. It's either A or D. So what are the people in the classroom? What people in the classrooms think about? Like, what do you believe? What do you guys believe?
I think we need
I
to
agree.
find execution times.
So,
And
okay,
then-
why do we have to find execution times?
Because when we need to measure the performance difference, we'll focus on the execution times. Like that's the metric we need to use.
Okay, so how do you get it?
Yeah. So total execution time.
Okay, so for
execution time-
machine X, for machine X, is it the same with the previous one?
Yes, it should be 2.5.
Okay, so this one we
sec-
can ignore it for now, right? How about Y?
It should be, I calculated as 2 seconds.
Okay, 2 seconds, right? So then given this execution time, how do I get my speed up?
I think execution times, like if we want to calculate how much faster, we should it's like
Reciprocated.
reverse order. So execution
Reverse
time
order.
of x, yeah, reverse
So we
order.
can
Execution time of x divided by y,
But why reverse?
because it's in reverse. Performance is in reverse relation with the execution time.
performance.
Okay, so I'm not satisfied with the answer. Where in a book define the speed up, or what does the book say about speed up?
I think it's a difference between execution times, like how much like the percentage,
It's the difference.
like difference between execution times divided by the execution of x.
So what
So-
answer do you get here?
In the book, it's like I think chapter 1.9, speed up overall is equal to execution time old divided by execution time new.
Okay, so is that the same as the one that you guys mentioned here? It's not the difference divided by the
Yeah.
baseline,
It's-
right? So that's why
it's-
we are saying, right? We need to make sure that everyone is on the same page before we can move on. Okay, so listen carefully. There's only one, the only one definition of speed up in the world of computer architecture. There's no other definition of speed up in computer architecture. Again, there's no other definition of speed up in computer architecture. That's the only equation that is valid. Anything else is not considered as speed up. So whenever I said what one is faster than the other, when I say what's the speed up, that's the only way of calculating it. So if I want to say X is the baseline design, Y is the improved design, and I want to say Y is n times faster than X, that's the only definition. So, or the other thing, you can say the speed up of Y over X is the execution time X over execution time Y. And the reason is because of the performance is the reverse of your execution time. So that's the reason, but that's the only definition of speed up. There's no other definition of speed up. So based on that definition, right, we got the execution time Y equal to 2 seconds, then divided by the execution time. With the old execution time, X divided by the new execution time, that's the 1.25 times. And again, this is the only definition that is acceptable in this class. All other definition does not count. And every architect would tell you this is the only way of calculating the speed up. So what you guys describe using difference divided by baseline, sorry, that's totally not acceptable. And if you show that kind of answer in your midterm, I will 100% for sure, I will give you 0 credits on that, because that's the very, very basic thing in computer architecture. All right, so with everyone on the same page, right? What really important as a computer scientist, computer engineer, you want to know what are each factor in your program, in your system would affect your performance. So let me ask you a few things. So as a programmer, who you are, right? How many components in a performance equation do you think you have an influence on? Yeah, I just muted myself when I describe the answers?
No, sir. It's fine.
What?
It was fine, sir.
Okay. All right, looks like everyone is pretty much put their answer in. So let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so, so looks like most of you think the answer is either B or C. So let me see. Why don't you guys go ahead and discuss with your friend and see what do you guys think after discussion. All right, so let's go ahead and discuss in groups. And I want to hear people in person or people in the online can also have their answers. Okay.
Okay, why'd you say instruction count? You think you cannot affect instruction count? You can. It's the other two you cannot affect. So let me say like cycle time. What's that related to? Yeah.
All right, let's wrap up in 15. Oh, shoot, I should have the. All right, let's try to wrap up our discussion. If you haven't voted, don't forget to vote. Okay, don't forget to vote again. All right. Wrap up in 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, we still have a lot of advocator on either B or C. So I really like to hear what you guys think for this particular question. What do you think as a programmer you can affect? Can someone share your thoughts with us?
As a programmer, I think we can alter the instruction count.
Okay.
But then I'm not sure if the programmer can alter the clock speed to alter the clock cycle time. So I'm going with 1.
Okay. What about others?
I think that because there's different types of instructions, we can change the kind of instructions we have. So
Mhm.
if we can adjust the number of instructions, and we can then also adjust the type of instructions. So I think as a programmer, we should be able to choose two types.
Okay. So here's the thing, right? So sometimes when you implement the same function, but if you have a different algorithm or a different instruction count, different optimizations, typically you not only change the instruction count, but also the cycle time. But I want to say for this particular question, the answer is probably all of them. So, but let's look at this example first. So for this example, right? So I have two programs and there's version A and version B. So do you guys agree with that version A and version B, they all perform the same features? They would exactly get the same result in terms of the arithmetic result. Are they going to be the same?
Yes.
Yes.
Yes, they are going to be the same. How about the complexity?
Complex, I think. Same.
Yeah,
The
complexity
same,
should also be
right?
same.
Okay, so now let me show you the demo and let's see how this program will how these two programs with the same complexity, they pretty much do the same thing, right? And let me show you how they would perform
I think
differently
their
on
memory access pattern is different. That's optimization.
Okay, so let me show you, right, like how this programmer's multiplication would make difference. So this is the pieces of code that I'm going to run, and the only difference is this matrix addition loop. And one goes I first, the other goes J first, but you should all agree that it's going to generate the same result, produce the same amount of memory accesses. So that's make it and run it. So let me run, oops. Okay, so I forgot to put this. Okay, so let me run this version A and B, and let me put a time here. Okay, so let me run this two programs, right? Okay, so for version A, it takes 0.8 seconds to run. But for version B, it takes 1.3 seconds to run, right? So what's going on? What the programmer changes in this program?
So I think version
I
one
mean, this
access.
is a question. This is a question. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after the first run, most of you pick the answer as B. So I wonder what's the B that you guys have in mind. Can some of you unmute yourself and tell me what's the answer you have in mind. Like what's the B?
Okay.
What's that one?
CPI, sorry.
CPI. How do you know? Why is it CPI?
Because in the A, it's traversing the rows first, but in the B, it's going for the columns. So count per instruction would be higher for B. So yeah.
That doesn't explain my question. So why is it CPI? So the question is asking about how can you tell if the CPI make the performance difference? So how are you going to convince me and others it's the CPI?
My understanding is if we change the memory access pattern, then
Okay, that's actually not explaining what's going on here. Right. So a lot of cases when you guys saying that I put this answer, you should give me correct. But like if you start in this way, that's not what we are asking, right? So we haven't talked about memory at all. And just through the analysis, performance analysis that we gave you, how can you tell this is because of the CPI, not because of the instruction count, right? If you say, well, changing the memory order, can it change instruction count, right? Can it change the cycle time, right? You need to say, why is it not cycle time? Why is it not instruction count? Right? So for this
my
particular question, okay.
For CPI, so it's like because we change the memory access pattern, each time we access
No,
some
that's
memory
actually
location.
not, but that's actually not a convincing answer for this question. Because that doesn't explain why the CPI changes here. Well, why you can tell is the CPI changes here. How can you show me it's just because of the CPI make the performance difference, but other things remain the same?
I actually selected all of them.
What?
All of them.
All of them?
Yes.
That's also not the right answer. Okay, so again, right, to answer this kind of question correctly, right, especially in your assignment, in your midterm for sure, I want to see this kind of analysis. And again, this is a great level course. We want you to learn a scientific, systematic way of analyze your application performance, right? So, so a lot of, well, so I just had a comprehensive exam for the student last quarter, and I checked the exam, but a lot of it apparently still didn't get what I really want to see in the answer of their question. So this time, I hope you guys are walking through this example and carefully know what am I talking about, right? So the question is asking what's really the factor affecting the performance, right? So you have to prove it's not CPI, it's only CPI, but not instruction count, it's the clock rate, right? So first of all, do you guys all agree that the complexity are the same? And second thing, how about the instruction count? Are they going to have very different instruction count? Is the instruction count going to be different? For these two loops, are they going to have the same instruction count, similar instruction count, or very different instruction count?
I think it will be the same.
It will be
They
same,
will pretty
actually.
much be the same. How to prove that?
I think depends on the compiler.
Saying it's the same compiler, how are you going to generate a code?
It's upon the array size. It's the same.
Say again?
It depends on the array size, right? So it's the same for both programs.
It's the what?
Array
Talking about
size.
the array size.
No, That's not relevant. Because if you check about the way how we calculate the index of this matrices, it's pretty much the same, right? So again, you have to definitely check carefully in your assignments and the assigned readings. So for the SAT-6 to interpret this inner statement, it's not too different because they are essentially the same statement. So it's not going to be different. And the amount of iterations that we will generate here, right? That's why we have that example in the very beginning. If you check the loop, it's only related to the array size, right? So here you're going to have exactly the same amount of iterations for this inner loop. And the compiler does not do too much of the cross iteration optimization if they are not confident. So the instruction count for these two programs, they are going to be the same. And this example is run on exactly the same processor. So the clock rate is probably pretty much the same. So the only thing that you can see such a huge difference in performance is just because of the CPI, right? So that's why the question of this answer will be CPI, but not others, because you are able to prove that instruction counts are not changing, the cycle time are not changing. And another thing, another evidence that I can show you is that we can use profiling tool to demonstrate that. So so now I'm running a profiling tool here. So for the profiling tool, you can use perf-stat. That's actually on you can install it on a Ubuntu machine. And the perf-stat would actually give you statistics about how many cycles, how many instructions, and how much time that we use when we execute the program. And as you can tell, for this particular program, the CPU cycle time is pretty much about the same. It's about 5 gigahertz. There is some small dynamics, but it's not the main factor affecting your performance. And in fact, if you look at the one that runs faster, its cycle time is slightly slower. So that's not a main factor. In terms of the instruction count, the one runs faster has 16 billion instructions. And also for the one that runs slower, it also have pretty much the same instructions, right? So a lot of you saying that, okay, it will depend on the compiler. No, it's not related to that. And as long as it's the same compiler, this kind of code would typically generate the same amount of instructions. So when you talk about things, you have to base on science, right? So what really difference is you can see the number of cycles, and that gives you the average, the very different instruction per cycle, which is the reverse of CPI. So what really tells you is that for this particular question, particular example, programmers change the CPI. And the one on the left-hand side is better. The one on the right-hand side is worse. And why the CPI becomes different than some of you answer talking about, okay, it's about the memory access pattern. That's the answer I want when I ask why the CPI is different, right? But here, the question is that what the programmer changes to make the performance different, then the answer is CPI. So, and why is it CPI? Because instruction count remain the same, clock rate remain the same, right? So that's the answer we want to hear, and that's the right way to address the answer. And this is a very important technique if you are going to have interview with others. A lot of people saying that, well, I did my interview very well. I try to answer question in a way that I tell the interviewer, oh, what I know. But, you know, like when I hear some interviewee is not giving me the answer that I exactly want, I would feel that's a pretty big red flag in terms of effective communication. So hopefully this run of example will give you a very good idea regarding what I'm asking for. So for this particular question, CPI is the only right answer that would be acceptable for this particular example. And I hope the analysis that I provide will convince you on that. All right. And finally, for this particular question, can you also tell me by adding a sort, what the programmer changes in performance equation to achieve better performance? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so we still need some kind of group discussion for this one. So why don't you guys go ahead and discuss in group within very short period of time. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, more of you think it's D. So, well, because we are running out of time, right? So again, you should do a very complete analysis. And the thing is, we are asking for better performance, right? So if you think about if when option is 1, then when option is equal to 1 or 0, and if we again put this instruction count, cycle time, and CPI together, right? When option equal to 1, the instruction count is actually going to be more because you are adding the sorting function in there. And when you have more instruction, it actually makes your performance worse, right? So that's definitely not a factor. So what would really make the performance better is because we have lower CPI. So the answer to this question should be just A, the CPI. All right. So if you didn't get it right, please spend some time to get it to review it again. And before you leave the classroom, there are several things that I want to let you know. So first of all, we have another reading quiz due next Tuesday before the lecture. This Thursday, we also have assignment 1 due, and assignment 2 will be up this evening and due next Thursday. And the office hour tomorrow will be likely online, given the rapid test result that I have this morning. I'm pretty negative that it will be positive. It will be, well, I'm very negative that it will be negative tomorrow. So it should be online tomorrow. And the lecture Thursday, I will say it's safe to be online, but I will put someone in the classroom. So if you want to attend the lecture in the classroom, we will still have the lecture broadcasted through the classroom. And check our website for slides and grade scope for quizzes and assignments. I will see you on Thursday and hopefully see you in person next week.
In love, fighting against all odds, I know we'll be alright this time. Darling, just hold my hand, be your girl, you'll be my man, and I see my future in your eyes. Well, baby, dancing in the dark with you between my